Are you ready, Andreas?
Yes, I'm ready.
Okay. Hello, everybody. Welcome back again to Probability and Analysis webinar. Today, our speaker is Andreas Defant from Oldenburg University in Germany, and he's going to talk about George Boole meets Harald Bohr. Please, Andreas, feel free to start.
Thank you very much. So let me first of all apologize for this delay. I simply didn't know that there was a time change. I'm really happy to be here. And I mean, up to some point, it was a happy surprise when Pata invited me, because I mean, mathematicians usually belong to different bubbles. And I mean, I thought, okay, where's the contact? And then, but during preparing this talk, during the last weeks, I saw that there is a lot of contact. I mean, I even saw a very nice online talk of Pata on some connection. And then I decided that I would like to provide a quite wide range in my talk. So ranging from something which is almost connected, almost connected with Riemann's conjecture, and then at the very end we will be with Boolean functions and even this Aronson-Ambar-Ainis conjecture. So I mean, the two heroes of my talk, local heroes of my talk, this is George Boole. So I mean, a man way ahead of his time, and maybe I mean, he's certainly much more known than Harald Bohr. This is Harald Bohr. I mean, looking at their life dates, you can see that they never met. I mean, but I want them to meet here as mathematicians, of course. I mean, Harald Bohr, he was a great, I'm sure that he was a great personality. I mean, he was a great mathematician. I mean, he did this theory of almost periodic functions. All his life, he was working with Dirichlet series and very much connected with almost periodic function. He was a great teacher, according to his students. He was a great brother. I mean, his brother is Niels Bohr. He was an activist. He was Jewish. He belonged to a Jewish family from Copenhagen, and he was really fighting against the Nazi regime during this very difficult time. And he was a football player. I mean, here you see him. I mean, when he was 20 years old, I mean, here, I hope you see my cursor. I mean, this is Harald Bohr. I mean, he was playing in the national team of Denmark, and still, I mean, some people told me he's known as a football player, maybe even more than as a mathematician. I mean, this was 2 years before he defended his PhD. I mean, they went up to the final and lost this final against England. But so 2 years later, he started his PhD project together with Landau in Göttingen. And okay, here, I mean, this is some sort of advertisement. I mean, I together with my co-authors, you can read here. I mean, we wrote a book connected with the problem. So the leitmotif of this book is a problem posed by Bohr. And then, I mean, finishing this book, I saw together with Mietek Mastivo and Antonio Perez that there are some connections with the Boolean cube. Okay, so yeah, I will be mainly talk about some topics which are in this book, and I mean these two papers. Okay, so in his PhD thesis, Bohr worked on what is called the absolute convergence problem for Dirichlet series. Here you see a Dirichlet series. What is a Dirichlet series? I mean, it's just a series. You have these coefficients here, an, and you have this complex variable. And of course, the theta function, where all the coefficients an are equal to 1, is the most famous one. Yeah? And I mean, I read that like every young mathematician working in analysis at this time, they tried to understand that they wanted to solve Riemann's conjecture, and they started a systematic theory of Dirichlet series. And if you do this, I mean, the first thing you learn about such a Dirichlet series is that it converges on half planes. I mean, there is some abscissa, the abscissa of convergence, so that on the right side of this abscissa, in this blue area, whenever you take an S, a complex number in this right half plane, I mean, starting with this abscissa sigma c, you get, I mean, the Dirichlet series converges, and it converges against the holomorphic function. So you have a limit function which is holomorphic. Every Dirichlet series on such a half plane defines, I mean, the half planes can be the zero set, of course, but I mean, so if there is such a convergence, you get a holomorphic function. But there are other interesting half planes. I mean, there is an apparently smaller half plane from which on the Dirichlet series converges absolutely. And there is even a third half plane from which on the Dirichlet series converges uniformly. And one problem Bohr handled was, I mean, how big can the width of this strip on which the Dirichlet series does not converge absolutely, but converges uniformly, how large can this width be? Yeah? So this is the absolute convergence problem of Bohr. I mean, so S, I mean, this symbol S stands for the largest width of all possible Bohr strips. You look at all Dirichlet series, you calculate the width of this so-called Bohr strip, and then you take, I mean, of course, the soup of this. So the largest strip on which you have the largest possible strip of this type. Okay, and the first thing he found with a non-trivial proof was that this strip is less than 1/2. Less or equal than 1/2. Now the proof is much easier, but for him it was complicated because all of this happened during the advent of functional analysis. I mean, there was no functional analysis. There was not, I mean, not really a Cauchy, so a Cauchy-Schwarz inequality, which is behind this 1/2 here. Okay, so I mean, this tells you whenever you take a Dirichlet series which converges on one line, if you go 1/2 to the right, it converges absolutely. Yeah, and I mean, he didn't know any Dirichlet series such that these two abscissas are really different. I mean, so not a single example, and it was Toeplitz with a non-trivial proof who proved that the strip is always bigger or equal than 1/4. And the proof of Toeplitz, in fact, is quite interesting because Toeplitz looks at the smaller strip. He just looks at Dirichlet series such that every non-zero coefficient has an index so the index is just a product of 2 primes. So he just looks at 2 homogeneous Dirichlet series. So all a coefficient an is different from 0 if the index is the product of 2 primes. Such a Dirichlet series is called 2 homogeneous. And for 2 homogeneous Dirichlet series, the strip is already bigger than 1/4. So of course, if you look at less Dirichlet series, the strip is smaller. Okay, and then, I mean, quoting Bohr, in order to solve the absolute convergence problem for Dirichlet series, we need a deeper understanding of the theory of power series in infinitely many variables. And when I saw this the first time, I was surprised because, I mean, what is the connection of Dirichlet series with power series in infinitely many variables? Okay, and this is, you see this here. I mean, you will see there is nothing, this looks a little bit strange, but there is nothing to prove here. I mean, we call it Bohr's vision. And the point is, that maybe we first of all look here. I mean, this is just a multi-index, and so a finite sequence, all entries are natural numbers or 0. I mean, every such multi-index, you can define z to the power alpha, which is this thing here. I mean, applied to a sequence of, of complex numbers. And here you see the prime number decomposition of n. I mean, for every n, there is a unique alpha such that n is equal to p to the power alpha. Okay, and now what do you see here? You see here formal power series. You just see the blue coefficients. I mean, but you look at them as a power series. I mean, here you just see the coefficients an, but it's a formal Dirichlet series, no convergence. So we have to assign to every C alpha some coefficient an. And how do we do this? I mean, we want to define an we look at the prime number decomposition of n. So for every n, there is a unique alpha, and then we take the C alpha. And so we get a one-to-one correspondence between such formal power series and Dirichlet series. And so, I mean, okay, you might think that this is useless, but it's not. I mean, there's a lot behind this, and there's of course nothing to prove now. I mean, this is a one-to-one, even an algebra homomorphism between all formal power series and all Dirichlet series. It's interesting that, I mean, 5 years earlier, Hilbert wrote a very interesting paper, Goals of an Analysis with Infinitely Many Independent Variables. I mean, this was when Bohr was playing football still, so five years earlier. And he says in dealing with it, so with it, I mean, these formal power series, there is the risk of losing ourselves in too difficult or vague discussions without any corresponding gain for deeper problems. So nonsense. I mean, but if we do not let such considerations put us off, then as a reward waits for us the beautiful prize of a methodic unified vision of algebra and analysis. I mean, he somewhat says, I mean, for me, this sounds like, I mean, if you really work on this, I mean, then functional analysis could appear. Yeah? Okay. So then nothing happened on this problem of Bohr. I mean, the problem of Bohr was, how big can this strip be? I mean, the strip of a Dirichlet series on which the Dirichlet series does not converge absolutely, but converges uniformly. And Bohnenbluth and Hille, they proved the strip is 1/2. I mean, remember that the strip is always less or equal than 1/2. So it is equal to 1/2. They really constructed a Dirichlet series such that the strip is equal to 1/2. Yeah? And using this vision I just explained to you. Yeah, and I mean, the proof is, as I believe, non-trivial. It has a lot of nice features. I mean, for example, there is something called, which we now call Bohr's theorem, which tells you that, I mean, there is also an abscissa from which on the limit function created by the Dirichlet series is bounded. There's a largest half plane from which on the Dirichlet series is a bounded holomorphic function. And I mean, this abscissa is in fact equal to this abscissa of uniform convergence. So this is Bohr's theorem. And then there is Diophantine approximation, there is Kroneck's approximation theorem, the prime number theorem, and the Bohnenbluth-Hille inequality. I mean, they really proved the Bohnenbluth-Hille inequality to show this result. We call it Bohr-Bohnenbluth-Hille theorem because Bohr showed S is less or equal than 1/2 and Bohnenbluth-Hille equal to 1/2. I don't tell you now what the Bohnenbluth-Hille inequality is. I mean, I listened to a talk of Pater, and there was one moment where he asked his audience, does anybody know in the audience what the Bohnenbluth-Hille inequality is? And there was no response. So I expected you know what the Bohnenbluth-Hille inequality is. But it will come later. Let me just tell you that, I mean, they showed they graduated the problem. If you look at all M homogeneous Dirichlet series, so and a Dirichlet series is M homogeneous if only non-zero coefficients appear which have an index which has M prime numbers. I mean, if you look at this smaller strip, these are then the strip is M-1 divided by 2M. I mean, for those who know the Bohnenbluth-Hille inequality, this is the conjugate of this index which will appear later. Yeah. Okay. So I told you about this Bohr's theorem. A very nice Banach space appears here. I mean, all of this happened before functional analysis. There is a very nice Banach space. I mean, defined by SAPE. So you look at all Dirichlet series which converge and define a bounded function on the right half plane. This is some sort of Hardy space, as you will see later. So all Dirichlet series, they converge on the right half plane to a bounded. So this function is always holomorphic, but in this case, it's bounded. And I mean, you take as the norm, the subnorm on the right half plane. And then it's non-trivial to show that this is a Banach space. But if I come back to this Bohr-Bonnet-Hille theorem, I mean, this is this theorem here, that this strip is 1/2, then you can rephrase it. I mean, you can say, I mean, a Dirichlet series belongs to this Banach, if it belongs to this Banach space, then, okay, it's bounded from the imaginary axis on. If you go 1/2 to the right, then you have absolute convergence. Plus an epsilon, because these scissors are defined up to an epsilon, as you might imagine, of course. Okay, and this is a sort of L1 multiplier theorem of course, the objects in this H infinity. And then, so this is just a reformulation, which I repeat here. And the problem then appeared, can epsilon be equal to 0? And the surprising thing was, the answer is yes, but even more. So, I mean, there is this theorem. I mean, I call it Bohr strips under the microscope. So if you take a Dirichlet series in H infinity, so a Dirichlet series convergent on the right half plane, which defines a bounded holomorphic function on the right half plane, then you always have this estimate here. I mean, you see there is no epsilon, not any longer an epsilon. Epsilon is equal to 0, but you have this strange term here. So you have more even, and in many respects, I mean, this is the optimal theorem. I mean, this is really the outcome of research which took a long time. For me, it starts with Bohr, it goes on with Littlewood, then Bonnet-Hille, Kefelec, who, I mean, there is a big gap, as you can see here in time. It was Kefelec who started again, then Konyagin and Kefelec went on, and then people from probability theory, a lot of, so there's probability theory behind this, but also a lot of analytic number theory. And then in a paper which, so I wrote together with Frerick, Ortega, Uranais, and Sape, and this was published in the Annals of Mathematics. We finally got this result. But I mean, we would not have gotten this result without the previous work done by these people here. So it's really, it marks the end point.
Does it have something with iterated logarithm in probability?
No. The probability part is no. I would say no. The probability part is really the Kahane-Salem-Zygmunt inequality. Yeah.
Okay.
I would say no. Okay, but going on, I would like to explain that this result here, which you see here as a sort of multiplier theorem, this is something on Sidon constants. I mean, because I want to all the time touch Sidon constants. I mean, you can rephrase it. I mean, here you look at the quotient. I mean, here you look at a finite Dirichlet polynomial, a Dirichlet polynomial of length x, and the quotient compares the L1 norm of the coefficient and the norm of this Dirichlet polynomial. So, and this is this number which you just saw. Of course, now you cannot understand, maybe you cannot understand why this is a sort of Sidon constant. Where is the compact abelian group? I mean, if you think of the definition of Sidon constants. But before I explain this, I would just like to show you something which is still mysterious for me. There is a famous conjecture in number theory which shows exactly this strange term here. And the conjecture is that if you look at the theta function on the critical line 1/2, on this interval here, so the left side, you take the subnorm of the theta function on this critical line on this interval from 0 to x, then you get exactly this term here. And nobody knows what, I mean, is this a coincidence or whatever? Yeah.
But in the first formula, it should be x, not n in logarithms, right?
Yes, sorry. This is a misprint. Yes, right. Yes. I hope, so here it was okay. Yes, it should be x. Okay, but let me try to explain you where the group is here. I mean, there is a paper of Hedenmalm, Lindquist, and Sape, which marks the beginning of the modern theory of Dirichlet series. And the statement, I keep the statement a little bit vague, But I mean, here you see the infinite dimensional torus. So the countable product of the circle group, which is of course a compact abelian group, and the H measure is the Lebesgue, the countable product of the Lebesgue measure, and H infinity is just Hardy space. So all L infinity functions which have Fourier coefficients supported in the positive cone, say. And if you look at this Hardy space here, then this is isometrically isomorphic to this H infinity, and the coefficients are preserved in the sense of this Bohr vision. I mean, every function here is uniquely determined by its Fourier coefficients, and every Dirichlet series here is uniquely determined by its Dirichlet coefficients, and they are preserved in the sense of this Bohr vision. And then, if you want to rephrase this, here, if you look at this set alpha, so they are really characters on this group here, and you look at all characters coming from alphas such that p to the power alpha is less or equal than x. So this is a set of characters, these red functions, and here you compare what you do. If you look at Zedon constants, you compare the L1 norm of the coefficients with the norm of this analytic or this trigonometric polynomial here. Okay, so this theorem is in fact a result on Zedon constants. Okay, and in order to prove this, we had to improve the Boole-Broglie inequality. We needed a substantial improvement of the Boole-Broglie inequality. So this is the moment where I would like to explain the Boole-Broglie inequality. By this symbol, I mean all analytic trigonometric polynomials of degree less or equal than d. And the degree, that comes from the L1 norm, say, of the multi-indices. And the theorem says that, in these terms here, that if you look at this number 2d divided by d plus 1, then if this is p, then the LP norm of the Fourier coefficients can be estimated by the supremum norm of this polynomial f times a constant which only depends on the degree and not on the variables. And this exponent 2d divided by d plus 1 is the optimal exponent. So this is a very nice inequality. And I'm sure that when Boole-Broglie saw this result of Littlewood, this 4/3 inequality, I'm sure that then they knew how to prove this, solve this problem of Bohr, the original problem of Bohr. This is the 4/3 inequality of Littlewood. Some people claim that this is a sort of forerunner of Grotnick's inequality. Okay, because I'm running out of time, so I would like to go on. I would like to go back in time, again back to Bohr when he didn't know the solution to his absolute convergence problem. He says, in order to solve the absolute convergence problem for Dirichlet series, we need a deeper understanding of the theory of power series in infinitely many variables, according to this vision he had. It was in the course of this investigation that I was led to consider a problem concerning power series in one single variable only, which seems to be of some independent interest. And this is the moment where I would like to switch to Bohr's power series theorem, which he looked at because he wanted to solve this problem on Dirichlet series. He wanted to show that the strip is 1/2. And he came up with this here. With this here, this is this nice, in a sense, little theorem. If you have a holomorphic function on the open unit disk, then this inequality is true. So this 1 divided by 3 to the power n is an L1 multiplier with constant 1 here, with constant 1. And this one thought, this is the so-called Bohr radius, is the best possible thing. And Bohr was only able to show 6 instead of 3. But in the paper he wrote on this power series theorem, he says that Landau, Ries, I think Landau, Ries, and Friedrich Wiener, this is not Norbert Wiener, I mean, they told him how he could improve his inequality from 6 to 3. And the strategy was, Wiener suggests, and Bohr then published the proof of Wiener. So if you have this holomorphic function, and these are the Taylor coefficients here, then the blue inequality is really the thing one has to prove. Because the blue inequality, which has a very elementary, nice proof, gives you that the modulus of the coefficients are less than this thing. And whenever you know this, you just can estimate this sum here. You take out the 0 coefficients, and then you estimate all the coefficients by 2 times 1 minus the modulus of z0. Then you get this thing here, and this is 1. It's magic, but now there is, I mean, there is now really a sort of industry on these on papers working with these looking at this power series theorem of Bohr. Okay, again here I put the theorem. I want to rephrase the theorem in terms of Fourier analysis, and it's very simple, because I mean we all know that the H infinity on the open unit disk and the H infinity on the distinguished boundary, they are the same, and I mean the isomorphism preserves Taylor coefficients and Fourier coefficients. So if you can rephrase it simply in some result on Fourier coefficients. I mean, if you take f in this Hardy space, then you have this inequality, and the constant is 1. I mean, this is really a point. This is some sort of isometric thing here. Okay, so what we then started, or with other people, Boas, for example, Harald Boas and Dimitri Kevinson from complex analysis. I mean, we got interested in multidimensional Bohr radii. I mean, and what is a multidimensional Bohr radius? I mean, you look at functions in n variables, and then you rewrite the same inequality, now r to the power of the order of alpha, and you want to know the best r here. I mean, so then you immediately see that if n is equal to 1, if n is equal to 1, this is 1/3, and this is the only precise value known here. I mean, the only precise value. So the major problem then for some time was, I mean, what is the asymptotic behavior of these numbers? And I'm convinced that, I mean, Bohr up to some point had this definition. I mean, he didn't write it explicitly, but he knew that if I can show that these numbers go to 0, then this absolute convergence problem, I mean, then the strip would be bigger than 0 at least. So there is a very deep connection between this and this absolute convergence problem. I mean, here I put a picture which I like very much. I mean, you see the two brothers. So Harald Bohr is on the left and Niels Bohr is on the right. And I mean, you know that the other one also defined a radius. I mean, if you go to Wikipedia, then this is called Bohr radius. And you can see, if you look at the face of the little brother, what he thinks about the Bohr radius of the older one. I mean, he's not convinced that this is the right one. Okay, so how to attack this problem here? I mean, this problem, how to attack it? I mean, I just give you a little sketch. I mean, we look at, I mean, when we try to attack this problem, we look at building blocks of functions here. I mean, we take some subset and look at this Bohr radius. Now we just want the inequality for less functions. So the radius is bigger, okay? And so you see, if you look at all functions, I mean, looking at this definition, then you get the Bohr radius for n equal to 1, which is 1/3, the old thing. And so find the asymptotic decay of this KFN for characteristic building blocks. What do I mean by characteristic building blocks? I mean, I put some here. I mean, this red thing is the thing which we are really interested in. What is the Bohr radius of all functions? And I mean, it's very simple to show that if you just look at polynomials and say you use this symbol for the Bohr radius with respect to polynomial, you get the same thing, the same asymptotic. It's less trivial if you look at only at homogeneous polynomials, so really less. And then this Wiener argument in several variables shows you that still you get the same asymptotic. And then we started to graduate the homogeneous, I mean by the homogeneity degree equal to D and lesser equal to D. So this is the Bohr radius of all homogeneous polynomials, of all D-homogeneous polynomials. This is the Bohr radius of all polynomials of degree lesser equal than D. And maybe I skipped. I mean, again, Sidon constants. I mean, if you want to know the Bohr radius of all D-homogeneous polynomials, then this is 1 divided by the dth root of a Sidon constant. I mean, here you see a trigonometric polynomial, and you compare its norm with the L1 norm of the Fourier coefficients. And 1 divided by the dth root of this is this object here. This is because of homogeneity. And this was very helpful because then we were able, again, on the basis of this Boole-Brusili inequality, to find the precise asymptotic of these building blocks. I mean, it's not so important that you now look at it. Yeah, I mean, this here means, I mean, there are universal constants up to a universal constant from below and above. You get this. At least you can really calculate asymptotically this thing. And the highlight which appeared, so for me, after years of research, is this here. So the original task was find the asymptotic of the Bohr radius. And the point is that this limit is 1. So I mean, the Bohr radius really behaves like root of log n divided by n. And again, I put the names. I mean, and all of them contributed a lot of things here. So for example, Boas and Kevinson, they proved that this limit is less or equal than 1. This is a probabilistic proof. So with this Kahane-Salem-Zygmunt inequality, and they conjectured there should be no log term. Yeah. So this is what they thought. And then, for example, I proved together with Leonhard Frerich in 2006 that there has to be some log term. I mean, we got log n divided by log n instead of this log n term. And then this is this paper in the annals which I mentioned. But the last step, again improving the Boole-Brusili inequality, gave that this limit is equal to 1. Okay. So now, again, this is the Boole-Brusili inequality in terms of Fourier analysis. And what is the substantial improvement? The substantial improvement is an improvement on the constant. I mean, here, the Boole-Brusili and Hille knew the constant is not depending on the number of variables. So this is then our notation of the constant, of the best constant, which of course has no n. Okay, and here I did some. I just show you how close. I mean, let me show you this theorem again. I mean, we wanted to prove this theorem, and this really shows you that. I mean, look first at this inequality. This is probability theory, Kahane-Salem-Zygmunt inequality, somewhat standard. I mean, here the lim inf is less than the lim sup, but on the left side, you see 1 divided by the lim sup of the dth root of this Boole-Brusili constants. So I mean, if you have very bad estimates for the Boole-Brusili constant, then you simply get 0 here on the left side, so nothing. So you really have to improve the constants. And since nobody before was interested in having nice constants here, I mean, Boole-Brusili just wanted some constant which does not depend on n. I mean, this is their constant. They were not interested. They wanted no n here on the right side. But then we improved it. I mean, in this paper, which I all the time mention, we got root of 2 to the power d, much better, if you would have time to compare, much better than this. And then using our techniques, I mean, elaborating in a non-trivial way our techniques, the best upper bound for the constant is now constant root d times log d. So this means that if you take the dth root of these constants, and the lim sup, then you get 1 really. And if you allow me to go back, I mean, then here below you have 1, and this is the lower bound. I mean, okay, now I want to approach Boolean functions. And so let me tell you something about Boole. I mean, I had this very serious picture. I mean, here is a picture. He was also a very cool person, as you can see. So in a second, I start to talk about Boolean functions, but allow me first of all to tell you that, I mean, you could now ask, is there a power series theorem in the real case? I mean, if you just look at the real polynomials on this unit interval, I mean, do you have this inequality here? Do you have this inequality? I mean, is there a real version of Bohr's power series theorem, replacing the disk, say, or the torus, the distinguished boundary, by this interval? No. I mean, if you look at this function here, I mean, then you immediately see that such a number r has to be 0. There is no r bigger than 0 or strictly bigger than 0, less or equal than 1, such that you have this power series theorem. No chance. So do you have a chance for the real Boolean-Hilly inequality? You just look at real polynomials, real coefficients, and you want to have this inequality. The answer is yes. I mean, because this is simple. I mean, if you have such a real polynomial, you just consider it as a complex polynomial, then you have the complex Boolean-Hilly inequality. Okay, then of course, if you use the complex Boolean-Hilly inequality, you have here so the torus, the n-dimensional torus, but you can compare the norm of the n-dimensional torus with the norm of the subnorm of f on the n-dimensional disk. I mean, there is a constant. I mean, there is a result of Klimek. I mean, if you compare the subnorm on the n-dimensional disk with the subnorm on this n-dimensional cube, you have to pay the constant 1 plus root of 2 to the power n. Sorry, d, not n, d. And then we prove that the best possible, I mean, here, I mean, the dth root of the best possible constant here, I mean, this indicates that I'm now looking at the best constant here, is in fact, so for large D, it's 1 plus, I mean, the dth root, I mean, this lim sup is 1 plus root of 2. So the real situation is really different from the complex situation. In the complex situation, we had sub-exponential constants, and here not. Okay, now Boolean functions. I mean, so there is no Bohr's power series theorem. There is the Boolean-Hilly inequality. So Fourier analysis of functions on the Boolean cube. I'm sure that in the audience there are many people who know much more about this than me. I mean, this is such a function on the n-dimensional Boolean cube, and I mean, as we know, it has many applications in these topics, and so, for example, here, even in quantum computation now, and as I learned some weeks ago, even in learning theory. Okay, an example here is this majority function, for example, well-known function of this type, an important function of this type. And I mean, when we started to work on this, I mean, the basic idea was that, okay, to understand these functions, you do Fourier analysis. I mean, you have this compact abelian group, and you know that every such function has a Fourier-Walsh expansion. I mean, here you see the characters, I mean, of this compact abelian group, and then you can define Fourier coefficients. They just depend on this subset S, and the Fourier coefficients you get integrating f against this Walsh function. So you have this Fourier-Walsh expansion. And okay, here you have a similar thing. I mean, this is Bohr's situation, I would say. I mean, you have a compact abelian group. You know that every function f in L1 is uniquely defined by its Fourier coefficients. I mean, and this is no equality, as we know. Okay, but there are these similarities, and the idea was, what can we do in this situation, coming with the techniques we know from, say, Bohr's world. I repeat here the Fourier-Walsh expansion, and I mean here, let me define the degree I mean, the degree is just the maximum of all cardinalities if the Fourier coefficients are different from 0. So if this degree is, this is a function which has degree less or equal than d, and then d-homogeneous functions would be, this Fourier coefficient is different from 0 only if the cardinality is d. And okay, again, the majority function, in this book of O'Donnell, one can learn that it's quite complicated to calculate the Fourier coefficients of functions. I mean, he has a little subsection in which he calculates the Fourier coefficients of the majority function. So our idea was, we define the Boolean radius. And the Boolean radius is just by copying the definition, say Bohr's definition. I mean, Bohr's Kevinson definition, Bohr, inspired by Bohr. I mean, which I repeat here. I mean, this is Bohr's definition once again. I mean, you see, for every f, you have this inequality here. And all we change is that we look at Boolean, we look at these functions on the Boolean cube for a subclass. And we write this inequality here. And the soup over all rho now. Okay? I will repeat this definition here. And then, for example, we calculated, one of the first thing was to calculate I mean, you can take a single function here. This is a subset of functions on the Boolean cube. We calculated the Bohr radius of the majority function. It goes to 0 like 1 divided by root of n. And we did this for larger classes of linear threshold functions. Okay, this also took us a little bit of time.
Well,
so what is our major?
One second, the last line of, yeah. What kind of integral from 0 to...
from 0 to gamma.
From 0 to gamma. So gamma is in the wrong place. Okay.
It's on the wrong place. Yeah, very good. Thank you. It's on the wrong place. So what is our major goal? Our major goal is to calculate the Bohr radius of subsets, of certain subsets which are nice. So for example, we were interested in the Boolean radius of all functions on the Boolean cube. And let me tell you, I mean, I would like to ask, is this a silly question? I mean, I just told you that there is no Bohr, there is no power series theorem of Bohr in the real case. Why should there be a hope that it makes sense to study this? I mean, the hope comes, I would try to explain the hope as follows. I mean, look at the blue function on the n-dimensional Boolean cube. Of course, the blue function can be, I mean, if you just look at this red function here, I mean, it's something on the n-dimensional cube. And since this is a function which is affine in each coordinate, you get that the soups are the same. So, I mean, the blue functions, the Banach space of all blue functions and the Banach space of all red functions, they are isometric. But here you do, I mean, if you look at the blue functions, you do not look at all polynomials. There's no Bohr radius for all polynomials. You look at a subclass of polynomials on the n-dimensional Boolean cube. So there is some hope that this notion makes sense. And okay, I repeat this here. And for what? I mean, this is some sort of propaganda, of course. I mean, is it possible that Bohr's world offers techniques which so far were unknown in Boole's world, and vice versa? I mean, we come from this Bohr, from the world of mathematical world of Bohr. I mean, can it help in the world of these Boolean functions? So, is there any hope to connect Bohr's world with fashionable topics like quantum information theory or even learning theory? Is there some hope that this transfer, does it make sense? Yeah. And so, for example, the first thing we got, I mean, if you look at all Boolean functions on the n-dimensional cube, then this Boolean radius can be calculated for every n, very different from in the Bohr case. I mean, just the first Bohr radius is known. It's 1/3. But here you can calculate it for all n precisely. Asymptotically, it's 1 divided by n. And I don't have the time to show you the proof, but I just want to tell you that this proof really works like in Wiener's case. I mean, you have to estimate the Fourier coefficients by 1 minus this Fourier coefficient, say the constant term, the expectation. There's no 2. And if you have this, you can start to estimate this sum here. And you take out the empty set, and then you stay with this term. You can estimate all these coefficients here, and then, I mean, you will find this number here. You can calculate it. I mean, I skip this, but okay. My message is Wiener's basic idea up to some point, at least the strategy, works. I mean, no probability theory. I mean, if you want to show that this is optimal here, then you really look at the concrete Boolean function defined here. Okay, and then I mean, then in this paper, what we do, we try to calculate again. I mean, what was done for Bohr. I mean, in the case of Bohr, the Bohr radius for all functions, this was this root of log n divided by n. For all homogeneous functions, also asymptotically, like root of log n divided by n. D-homogeneous functions, this term here, degree D functions, there's a sort of breaking point here. But here on the other side, we did the same. And so, for example, if one looks at these two cases, the Boole-Hille inequality is again needed. I mean, here you have similar behavior. It doesn't look, I mean, this asymptotically, these two terms are also the same here. But so here, a big difference. I mean, you can calculate them exactly. And the last thing also was complicated for us. I mean, in the degree D case follows from the D-homogeneous case in Bohr's world. But here, there is no good, the Boole-Hille inequality is no of help in this case. I mean, you really need hypercontractivity inequalities, which are, I mean, you know this better than me, known in the case of these Boolean functions. Okay. So what about similarities and differences? I mean, maybe I should also say in all cases, there is some sort of Wiener argument, different, but the strategy is still the same. And then in the second case, sometimes you can use the Boole-Hille inequality, sometimes you don't need it. And here you have to use really hypercontractivity. And okay, but what is the Boole-Hille inequality for Boolean functions? This was already known by Blei from 2003. He showed that if you look at the function on the n-dimensional Boolean cube, you have this inequality. You have the Boole-Hille inequality. But again, he was not interested in a constant. Maybe I should tell you that, I mean, if you want to prove this Boole-Hille inequality, you usually have to show a multilinear thing, and then you do polarization. The multilinear thing goes fine with respect to the constant, but if you do polarization, you spoil the constants. Then it gets, then you have to eat a lot of terms you don't want to eat. But then, of course, we needed again the d-th roots. I mean, we need good d-th roots of the Boole-Hille constants, and we proved this again. I mean, you saw this result already for functions on the n-dimensional torus. We proved the same thing for functions on the n-dimensional Boolean cube. Yeah, and I mean, we follow similar strategy as in Bohr's world, but we have to add some things. I mean, I believe some non-trivial things here. But you get again that if you take the d-th roots, then you get this one. And okay, I need 3-4 minutes more. I mean, there's a problem of Montanaro, who works on quantum information theory. He asked, I mean, is this Boole-Hille constant really bounded polynomially? Yeah. And I mean, it's even not known whether it's uniformly bounded, which is not so nice. So why is this interesting? I mean, I just want to sketch this because I even don't understand it here, every detail. I mean, there is a famous conjecture of Aronson and Amberinius of 2012, and they claim that quantum computers are much better than classical computers if a problem is structured, but this is not the case if the problem is unstructured, whatever structured and unstructured precisely mean. But I mean, they put a very precise Fourier analysis inequality. So if the answer is yes, then this, say, meta conjecture, which I just mentioned, this is a sort of meta conjecture, would be true. And I mean, here this compares, I mean, the variance of f divided by d up to a polynomially, so with the influence of the variable. So the statement is, for every f of degree less or equal than d, there is one variable which has influence. And so if too, this conjecture would have significant consequences regarding the limitation of efficient quantum computation. This is a sentence which I copied off the book of Orlando. And there are partial results. And I mean, this Boole-Brusselian inequality we have gives a partial result. I mean, so it's interesting that one result, I forgot the authors. I mean, if you can replace this d by 2 to the power d, and if you follow some arguments, which we typically do when we prove these Boole-Brusselian inequalities, you can prove this result. But a real consequence of this Boole-Brusselian things we have is that, I mean, if you look at functions for which the Fourier coefficient in modulus always have the same magnitude, and replace this d by this constant c to the power root of d times log d, then the conjecture is true. So there are some partial results, but I mean, probably the Boole-Brusselian inequality is, I believe it's not the right thing to attack this conjecture really. So so this is why I'm very happy about this paper here. I mean, the more links of Bohr's world with Boolean's world. I mean, the probably most exciting one, for me at least, is a recent result by Pata and his co-author Eskenazis from 2022, learning low-degree functions from a logarithmic number of random queries. I mean, I mean, Pata is much more competent here to talk about this. I don't want to talk about it, but I mean, for me, it's a very nice thing because I mean, we had the hope that this Boole-Brusselian inequality, I mean, we just proved it in the blue in some sense. Yeah, we thought, okay, this might be interesting, and it seems that there is some interest. Okay, I want to finish here. I mean, I wanted also at the very end, I wanted to tell you something about this person here. Maybe you might know him. I mean, Boole and Bohr both meet Banach, and because all this is also closely related with nice local Banach space theory. But I mean, I skipped this part here. I mean, anyway, since I mean this presentation will be online, so thank you very much. I go to the end. I mean, thanks for your attention. And once again, I'm sorry for this hour.
Thank you very much, Andreas. That was an excellent talk. Are there any questions?
I have some questions. For example, in this estimate of your c to the power square root of d log d, is it any importance of anywhere of what is c?
So of course our proofs give some c, but so I put c because I don't know any application which really needs this c.
Mm-hmm.
I mean, Pata, I don't know whether in your I mean in your estimate of the number of these queries, you just put the Boole-Brusselian inequality. So in principle, a good c also gives a nicer estimate there, but I don't know whether this really means something.
Yeah, it would improve the number of queries. You're right, but if we do better C, maybe better queries. But by the way, I wanted to ask: nobody even knows if Bochner-Bus relay is uniformly bounded by universal.
Yes, yes, exactly. This and I mean, of course, I mean,
and on the
this
torus,
is probably
on the torus too.
Yes. So nobody knows, and this is somewhat disgusting because I mean all the proofs are improvements of the original proof of Littlewood for the 4/3 inequality. All the proofs are improvements. I mean, of course, some of these improvements are not so trivial, but I mean the strategy is still the same. You prove some for a bilinear a multilinear thing, and then you do polarization. And of course, this can be done in a clever way and in a less clever way. I mean, people like Bohne-Hille, as I said, we're not interested in. I mean, there is some Blei inequality which helps to do this first step, this multilinear step. And of course, I mean, this improved already the constant very much.
Any other questions?
Got a question as well. It's a little bit unrelated to this Boolean stuff, but it's about the Bohr radius for polynomials on a polydisk, like in 2 variables, 3 variables, etc. I don't think they're known, like the optimizers or the value exactly for polynomials, but they're known in the single variable case. Do you know of kind of an approach that you think might be fruitful to pin down? Like it's a hard optimization problem even to do numerically, I think, because you've got to trade off.
You mean to calculate say K2, K3, K4? Is this the question?
No, not just K2, but K2 for polynomials. So K2 would be for all functions.
Okay, for polynomials.
Like,
Yes.
Yeah, I don't know. I played with it at one time. So I did a reading course with Dima Cavinson back in like 2014, and he gave me this problem, and I haven't seen anybody write anything on it, and it seems to be pretty difficult. This problem of trying to find the Bohr radius explicitly. It is computed for all polynomials, I think, for one variable,
exactly.
but 2 variable and up, it's not known.
Yes. So, but to be honest, I'm not. I mean, there is of course now a tremendous literature on Bohr's power series theorem for in one variable, and I mean there are results. So in one variable and for polynomials of degree less or equal than n.
Yeah.
But of course they are not precise. I mean, I mean, all I know is, I mean, for example, I mean, this Bohr radius is, of course, it's some sort of isometric thing. I mean, if you go back to the so for example, I mean, if you allow some constant here, sorry, I think for example, if you put root of 2 here, I think then the 3 is also root of 2.
Okay.
And this is optimal. So I mean, there's some sort of dependence. I mean, you allow a constant here, then this constant has influence on the radius. I mean, and Bombieri, I mean, I forgot the exact formulas. I mean, for some range of constants here, Bombieri proved a formula for the radius within some range. And I mean, there is deep paper also of Bombieri and Bourgain. So I mean, if you put a constant here, no, if you say what happens with the constant on the right side if the radius goes to 1? I mean, what is the asymptotic decay of the constant if the radius goes to 1? Also a complicated thing. I mean, these are the things I know, but I mean, I never. Okay, I have no good answer.
Yeah. No, thank you. Great talk. Thanks.
Thank you. Any other questions?
What is the second brother Bohr radius?
The second brother Bohr radius, I mean, if you go to Wikipedia, I mean, then the second Bohr radius is, I mean, the Bohr radius is a physical constant, and it's approximately equal to the most probable distance between the kernel of the atom, the nucleus, and the electron of a hydrogen atom in its ground state. I mean, I more or less read this now here. I mean, I even don't know. I mean, about this model of Bohr. How is it still? Probably it's still very important. But he was very important in physics, of course. I mean, he got the Nobel Prize for all this. But I don't know what physicists say about all this.
Thank you.
Any other questions?
Yes, I have a quick question. So, are there any vector-valued versions of the polynomial Bohr-Steele inequality?
There are vector-valued versions. Yes, I mean then you and there is a lot. And we have this in our book, yeah. And you immediately, I mean, you start to talk about type and cotype, of course, and so there are many things. I mean, there is even a vector-valued version. I mean, this is also interesting. I mean, and for this you need this. I mean, if you look at this 1/2 theorem here, no, sorry, this no. No, I mean the strip is 1/2.
Okay.
Okay, and what happens if you look at vector value direction series? So if the coefficients belong to some Banach space, and the nice thing is then the strip is 1 minus 1 divided by the best cotype of the Banach space.
Mm-hmm.
Yeah. So I mean, if you look at the scalars, then the best cotype is 2. So you have 1 minus 1/2. Yeah. If you look at L infinity, yes, I mean, you know, of course. So it's 1 minus 1 divided by the best cotype. So a number bigger than 2, of course, of this Banach space. And for this, you need vector-valued Boolean inequalities. Yeah.
And so at the level of the inequality, it affects the exponent or the 2d over d plus 1?
Yes. Yes,
okay.
it very much affects this. Yes.
Okay.
Yes. I mean, I mean, in this book which I mentioned, I mean, you would find a lot of things, and that there is a group. I mean, Pellegrino and Seoane and these people, they in fact worked on this. I mean, the Boolean inequality is of course also something for polynomials on Ln infinity or for multilinear forms on Ln infinity, but you can also do it on LNPs.
Mm-hmm.
I mean, and all of this gets complicated, and you get formulas for these exponents.
Okay,
Yeah.
thank you.
Haunan has a question. Haunan.
Yeah, thank you very much for the talk. So you also have a vector valued Boolean scaling inequality for the Boolean cubes?
No. Okay. So far not. But didn't touch this. Yes. I mean, I didn't work on it. I mean, I'm sure that some things can be done, of course, here. This must be possible. Yes.
Okay. Another question. So for the moment, the best constant for the Boolean cube case and the torus case are the same, essentially c to the power square root of d log d. And when applying to the Bohr radius or Boole radius, the resulting constants are different. Right? The Bohr radius and the Boole radius for degree d
they are different. I mean, yes, they are different depending on the set for which you try to calculate these radii. Yes, they are different. Yes.
So if you consider the same problem for different groups, for example, more general cyclic groups of order n, and you probably can prove something similar for Boolean inequality. And when applying this result to corresponding Bohr radius problem, then then the group
Yes,
structure
yes.
also
Yes,
affect.
could be true. Could be an interesting project. I agree. I mean, doing it for groups. I mean, what can you do for groups? I mean, yes.
Okay, thank you.
But so this is something I had in mind also, but never touched it really.
Okay.
Thank you very much.
I think we asked quite a lot of questions. So
Thank you very much for asking questions.
yes. Okay, I'll stop recording.